So, good afternoon, ladies and gentlemen. It's our pleasure to have Michele Zaccaron from Paris as the first speaker of the summer semester of the Nečas Center and Continuum Mechanics. So, Michele got his PhD in 2022 at the University of Padova, right? And then he had a chain of postdoc positions. In Dresden, Lausanne, also in Prague, with David Krejčíř at the Faculty of Nuclear Sciences and Physical Engineering, and now he is at the Polytechnic Institute in Paris. So Michele kind of is interested in modeling of waveguides and so on. So, and this will be also the lecture today. So we are happy to have you with us.
Thank you, Martin, for the kind introduction. Yes, and also a big thanks to all the organizers for giving me the possibility to talk and present my research at this seminar. So today I will talk indeed about waveguides, and this is my most recent topic of electromagnetic waveguides. So I guess we will deal with Maxwell's equation, and we will perform some geometric the deformation of the geometry of such guided structure, and we will see how does the geometry influence the spectrum of the Maxwell operator. So this is a joint work in collaboration with Philippe Brier, Maxence Cassé, Thomas Bonafos, which are all three from Marseille. And okay, without further ado, let's start. So if we take some all the objects, so that I may present to you a first main result of our research. So concerning the essential spectrum of the Maxwell operator, we will define everything, and then also some theorems, some results concerning the discrete spectrum, and finally also. The last few slides, I will talk more about geometric condition that a bit of this regarding the spectrometric study of waveguides. It started with more than between 30 and 40 years ago. I would like to mention one seminal work in this area by Exner, and Petr Sheba, both from here and from Czech Republic. And since then, so quantum waveguides deal with the underlying Hamiltonian operator. Let's say is the Laplacian. Usually, it's the Laplacian. So since then, there have been numerous results in this setting, and there continue to be. But shifted phenomena. So, for example, if one wants to introduce relativistic effect into the quantum system, for example, Dirac type of operators of Dirac type are a good model for that, and we fit actually in this area, so imposing electromagnetic systems. And up to my knowledge, there are not many people working on this. It's, I would say, very strong. There are not many people working. I would like to mention Nikolai Fibonov, which we will refer throughout the talk because we will use one of these theorems. Recent works, depends, but I mean, it's up to 6 years ago. Then us, and maybe I will mention also these people later on. So let's start off with the definition of a waveguide. What is a waveguide? We will work in R3. So for us, a straight non-twisted waveguide is just a tube, is a Cartesian product of the via line times a cross section, small omega. This is our notation. So for us, okay, small omega is a bundle simply connected Lipschitz domain over 2. So we have this kind of geometry, And now we want to take this tube and be able to bend and twist it. So this is these are our geometrical deformations. I would like to mention that these are do not alter the geometry, the shape of the cross section. But of course, one geometric deformation. So how do we bend and twist them mathematically speaking? The idea is to actually build a tubular neighborhood of a curve in R3 by means of this cross section, and then be able to rotate this cross section along it to create some twists. So we take a curve gamma parameterized by length C2. Okay, there is some regularity, and then what we do well, first I'm a so the curvature goes to 0 at each end, at infinity. And then, okay, what we do, what we want to do is to attach our cross section along the curve. So to do that, we need a frame adapted to the curve. Adapted means that follows the curve. One of the verses always a tangent. To be able to attach our cross section, and then a way to rotate this cross section. So I give you the word curve and frame. I guess all of you may think will think about frame. And it's not. I mean, we also started with that, but it has some limitations. For example, well, there are some regularity. One needs to assume more regularity on the curve. But most importantly, there is some limitation. For example, consider a straight curve or a curve that contains tangent is zero, tangent is constant. And so what we actually do is to use, in this kind of setting, is standard to use this called relatively parallel adaptive frame. It's also called Bishop frame, and I think Tang frame, but I'm not familiar. The idea is that, so adapted means that the first vector of the frame is always the tangent. And relatively parallel means that the two normal vectors, normal to the tangents, are always their derivative is always tangential. And so it's described by this differential evolution of the curve. And okay, so this K1, K2 are basically the intensity of the derivative along the tangent E1. And we can call them Bishop curvatures, and they're actually related to the real curvature of gamma by this equation. Okay, this is a compact form of the differential evolution. So this is what I said, and most important. So the idea is that the two normal vectors E2, E3, they only rotate on the tangent, only the necessary amount to remain normal to the torsion, if it's the torsion of the curve. But okay, so I don't want to spend too much time. One can find the more details here, and I would say so. This paper is very well explained. If you have a problem, just think of the frame. It is still, more or less we are there. And okay, now we are able to construct waveguides by just taking the map, this capital phi, from the straight twisted waveguide omega 0, the tube, to R3, just taking. I don't want to show you, but okay. And then I attach the cross section along the curve by means of the two vectors in the orthogonal plane. And as you can see, we can find this type of geometries. I want to show you also, again, going back to relative Bishop frame, frame. On the left, we have, so this is the base curve here is a helix. And I construct, I didn't construct, it's taken from this paper. But on the left, the waveguide is constructed by means of the Frenet frame, and on the left by the relatively powerful twist, let's say, or rotation given by the torsion. If it's the torsion of the head. So these are the assumptions. So the first is a condition, actually, so the diameter of the cross-section times the L infinity norm of the curvature must be strictly less than 1. So this is actually ensures that the map phi is a local single differential space. In fact, one ensures that the determinant of its Jacobian is always positive, bounded away from 0, and can be interpreted physically like a condition of local non-self intersection. So the curve cannot bend too much with respect to the diameter of the cross section, so that it self intersects. We want to avoid self intersections. Then it gets us that phi is a global one differential phase, and we consider the waveguide, let's say perturbed waveguide omega to be its image. So now we have a purely bending waveguide. We want to be able to rotate it, and how to do that? We introduce the rotating twisting function. Let's call it like this. Theta is basically you take a 2 a 3 on the cross-sectional plane, and you rotate the frame by intensity theta s. And so actually, we will call the derivative of theta will be denoted will be the twist of our waveguide. Now, bending and twisting waveguide by means of this other map, capital phi, is the same as the one I showed you before, only that now I implement E2 theta, E3 theta, the rotated versus, and so I can produce some twists. So, final assumption that we assume throughout the talk is that twist at infinity goes to a constant. Can be 0, can be not 0, but goes to a constant. So, a particular case, in a particular case, we can construct this type of geometry as a straight perturbed waveguide omega will be like this, bending and twisting. The only point is that assumption 1 and 3 tells us that at infinity, because I said at infinity the curvature is 0, and the twist goes to constant. I explained to you the geometry. Let's talk about the physical context. So, electromagnetic waveguides, we want to impose the Maxwell system. We will assume the waveguide to be a perfect conductor, so the walls are perfectly conducting. This is to define our boundary conditions. And filled with a material, okay, you may think about the vacuum. In general, is a linear, non-dispersive, homogeneous, isotropic material, but think of the vacuum. And so we can impose the Maxwell system. Here, I already used the constitutive relations that I need to use to make the Maxwell system closed. And I use the linear constitutive relations. Way, derivative time of E minus curl of H is equal to source term. Derivative time of H plus curl of E equals 0. Curl is the usual factor in R3. and divergence-free condition by the gaps slots. And okay, this is some initial condition in time, and this is given by the fact that we are imposing the perfectly conducting boundary condition, so that the vector field E is normal at the boundary, while the vector the magnetic field H is tangential. And again, you can assume epsilon 0 mu 0 to be 1 and 1. Since it's a homogeneous isotropic material, they become, in general, they're tensors. There's 3x3 matrix valued function tensors, depending on the position and maybe even depending on the frequency. But with our assumption, they reduce to a scalar function, which is, since it's homogeneous, it's constant. But I introduced because this one mu will become really matrix tensors, depending on these divergence-free conditions. Formulated in a rewritten as a Schrödinger type equation, the following. The pair of the electric field magnetic field plus IAU equal the source term and the initial is the Maxwell operator. So I introduced it here, at least it's actually operator with the 0, 0 on the diagonal, and mathematical terms. I need to define what does it, its domain, the base Hilbert space, the energy Sobolev space where it lives on, and so this will be done in the next minute. I will not. I will be very quick, but still I want to introduce the curl spaces. So this is the integration by parts formula, the green formula just applied to the curl. So you can flip the curl on the other side, and you have a remaining time on the boundary given by the tangential trace. F cross n will be called the tangential trace. H1 for the Laplacian, H1 Sobolev space, square integrable vector fields with weak curl also in L2. And so again, defined in a weak sense by flipping the curl on the other side with the test smooth compactly support the vector fields. In the same way, again, with the H1, H10, I can define the H0 curl space is in the weak sense the closed subspace of H curl of a zero tangential trace. So again, I can flip it on the other side against fields that actually they're not zero, that can be non-zero at the boundary. And there is also a strong formulation exactly at the same the case of H10 for the Laplacian by means of a closure with respect to the norm. Okay, so we take the pair EH in the space H0 curl times H curl. And the Maxwell operator A will be defined with this domain, exactly H0 curl times H curl in the, well, in the L2 space with 6 components. More general material with this station, this will give us a non-self-adjoint Maxwell operator, and so you lose a lot of structure. But for in our case, we are dealing with a nice operator, let's say, since it's self-adjoint, so we know the spectrum lies on the real line. But still, there are many challenges, so that I will show you. And okay, so L2 is this space of square integrable vector fields with this weight. In the case epsilon 0 mu 0, again, think of it as one is the standard L2 space. But I wanted to introduce it to you because I will eventually this epsilon mu will be modified and they will become really some matrix weights. So you change the metric, let's say. And so now the motivation is that we want to forget about time. If we look at the spectrum, what is its form? Where does it lie? Because information about electromagnetic waves along the waveguide. So information about the dynamics of the Maxwell system. Before proceeding forward, three conditions, but okay, we didn't forget about them. In fact, okay, first, dimension, so it has a very big kernel, and the fields with the boundary condition, the introduced in weak sense. Then we can see that the orthogonal of the kernel is exactly this solenoid substrate. So the real Maxwell operator corresponding to the physical Maxwell system will be A reduced, so which I denote paper to the orthogonal of its kernel. Okay, so this closes this part of the introduction. And now I'll talk to you about the first main result concerning the form of the essential of the Maxwell operator. Our waveguide bends and twists, but at infinity we assume this assumption, so that it's asymptotically straight and with a constant twist at infinity, at each end. And so this is the theorem. The essential spectrum of the Maxwell operator on such a waveguide filled with vacuum, if you want, is of this form. It's forming a symmetric gap around 0, with the threshold gap A beta, and generally depending on beta. In general, not explicitly dependent on beta, but in the case beta is 0, then we can really write A beta is the square root of the second Neumann Laplacian eigenvalue on the cross section. So second Neumann, or let's say the first positive Neumann Laplacian on the two-dimensional cross section. So to prove this kind of result, what we do actually is that we consider the waveguide that is fully, where k is fully 0, everywhere 0, so straight line, and the twist is everywhere beta, so a straight, constantly twisting waveguide. And thanks to a result by Filonov in 2019, we are able to deduce the full form of its spectrum of the Maxwell operator in such a constantly twisting waveguide. And then there is this general idea that the essential spectrum is not modified, it's not changed by compact perturbation. So morally, this is a compact perturbation of a constantly twisting waveguide. The essential spectrum only sees what happens at infinity, morally speaking. And let me give you some ideas of the tools and ingredients we use to prove this. So first, we pull back our problem from the perturbed geometry to the straight one, because we remember there is phi. So just phi equals the difference between omega 0, omega. Yes, I finished. And we pull back the problem from omega to omega 0 by means of the Piola transform. So-called Piola transform is a pullback. It's a unitary map from L2 with the standard weight of omega to L2 of omega 0, the straight waveguide, but with a different weight, different parameters, if you want, about the epsilon and ball mu. So here, J phi is the Jacobian of the diffeomorphism phi. And epsilon and mu, the new epsilon and mu, here in bold, are basically G minus 1, where G is this matrix here, is a symmetric positive matrix constructed with the Jacobian of the operator A hat. Now we have an operator acting on the straight waveguide with a different weight, or let's say with a different material, filling this the omega 0. Key point is that operator. So now with new parameters. Your problem. Preserves the domain, the solenoid subspace goes to the correct one. So the idea is that the initial geometry is now encoded. You flatten the geometry, you pull back, and now the initial geometry is encoded into the new material. So with the new electromagnetic parameters epsilon, bold epsilon, bold. We can do this procedure in the case, as I told you, of a waveguide where k is everywhere is equal to 0 and twist is everywhere equal to beta. So in this geometry, we have the Maxwell operator there. It's the vacuum. We pull back our operator. We have a Maxwell operator on the straight waveguide omega 0, where now the new coefficient epsilon, beta, mu, beta are particular, have a particular, let's say, characteristic. In fact, you can guess it from the color gradient that I used. They do not depend on the longitudinal variable s. So, okay, epsilon beta mu beta is basically g beta minus 1. G beta do not depend on s, only Y2, Y3, the cross-sectional variables. And this is exactly the case, the assumption of this theorem of Bashilonov. So omega b, the cross-section simply connected. Suppose that epsilon mu, which in general assumes to be a matrix value the fields, depending on the position, but not fully general. They do not depend on the position. Generally, they are independent on the s variable, only on y. So we are, of course, in the straight waveguide. Then it gives the form of the full spectrum of the Maxwell operator in such a setting, and it's purely essential. Actually, it's essential here is absolute continuous spectrum, and 0 is a point spectrum, but it's fully essential. And presenting a gap around 0, positive gap. And again, in the case epsilon mu trivial, 1, 1, or constant, then this was already known, in this case, was already known by sometimes, and you can find the proof, for example, in the trillion. In this case, the gap is exactly the square root of the second normal Laplace. That's where it comes from. This is done by actually separation of variables, and some of you heard of the term transverse electric modes, transverse magnetic modes. Okay, and so this is exactly the we can apply directly this theorem. And this theorem tells us that the Maxwell operator in this geometry is purely essential, and its spectrum has this form, forming a gap, symmetric gap around 0. Now, what we want to do is to our general waveguide, which at infinity resembles this. We want to see that preserves the essential spectrum. So how to do that? Now we want to compare the resultant of the perturbed one and the constantly twisting one. Still, at this level, we cannot do that because these two operators, they do not act on the same Hilbert space. So we need to flatten the geometry. So we implement another unitary transform. And it's brutal in the sense that you just flatten the parameters by taking the square root of the inverse of this G matrix. You do it for from both sides. Now we are on the same Hilbert space. We have that A tilde and A beta tilde, the pullback operators with this new transform VB and V beta are acting on the same Hilbert space, so we can do some resolvent comparison. The price that we paid is that we lost the Maxwell structure. So at this point, since these were kind of brutal, we lost the Maxwell structure, but still for our analysis, it's not. I mean, we managed to do, and we managed to provide that Birman-Schwinger type of principle. So I will not go into detail now. I don't have time. So the idea is that we do some Birman-Schwinger type of principle that, along the use of the analytic Fredholm theorem, actually we need a bit more the meromorphic Fredholm theorem. We can prove this type of result, so that the essential spectrum are preserved. Okay, and so this is the comparison in a picture. As I told you, we start from the geometry, but we pull it back in the straight geometry by the Piola transform, still preserving the Maxwell structure. At this level, we can use the Leonov theorem to know the spectrum of this, and we want to compare these two operators, acting one here and one here, or equivalent to these two, but still we need to get to this level, losing the Maxwell structure to be able to compare. Okay, but now I told you, you said to me, okay, you gave us this kind of problem is that does the geometric deformation create eigenvalues, which can be interpreted in a physical sense as trapped waves or trapped modes. So we are mainly concerned with the discrete eigenvalues, so isolated eigenvalues of finite multiplicity. And one can also get, I mean, in general, one can look at embedded eigenvalues that lie in the essential spectrum. So here I will do a bit the discussion will be reversed with respect to the previous section. So I will first introduce the strategy and then show you the result and comment the result, the main result. I thought it was more fluid, so hopefully it works well. So what we do is actually the strategy is that we pass to the second order formulation. So we take the square operator, actually of square of A curve. So it's important to work with the reduced one. So first, let me comment on why we pass to the second order formulation, because we want to use the language of quadratic forms, and in particular, we want to use the Mimax theorem, very powerful theorem. And so this is the quadratic form associated with this, and as you can see here, we are in the domain of the reduced operator, so in a much more regular space intersection with the solenoidal subspace. Moreover, we work in the particular case where the twist is zero, so only in a purely bending waveguide. We don't, in this case, to produce this result on the discrete eigenvalues, we don't twist. We only get a start from the tube and we purely bend it. This is well, also technically, because it gives us that this new epsilon mu, the new parameters, they are diagonal matrices. So it simplifies a lot the analysis. And the idea is to look a Rayleigh quotient, if you will, a Rayleigh quotient below the bottom of the essential spectrum. And because this is just application of the Mimax theorem, if we are below the bottom of the essential spectrum, then we know there exists at least one eigenvalue, one discrete eigenvalue. And let me comment on why is the bottom essential spectrum of this operator exactly this. Well, first we assume beta to be zero. Yes, we also work on the orthogonal, on the reduced operator. And this is very important because the spectrum, as I showed you, like this, passing to the squared, we have this A starts from A squared. So if we don't work in the reduced operator, the zero will still belong to the essential spectrum of the squared operator. And this is a problem because then at the bottom of the essential spectrum, we still will be zero. So we cannot hope to find out. The hope is to find an energy below. This is what actually complicates the analysis, but it's necessary because we want to find a test function which is more regular. So in the sense, we want more conditions because we want a test function not only in the domain of the operator. Okay, but what is the trial function that we use? Well, first we start with the trial function associated to this point here in the spectrum. So again, there is no square root because we work in the squared formulation. So this is called the transverse electric mode, and is built by means of the psi, a normalized eigenfunction associated with the second normal Laplacian eigenvalue of the cross section. Because this, okay, psi is a cutoff function. This is just to make this whole vector field n2, otherwise it wouldn't be n2. But forget about this psi for the moment. This is a generalized eigenmode associated with this point, with this value of the essential spectrum. You can build a bisequence that converges to this. And yes, so the idea is hopefully maybe we take the energy, the generalized eigenvalue that gives us this quantity in the spectrum in the standard case. So this is in the standard trivial coefficient, epsilon 0. But maybe if we perform a modification of the geometry, which means a perturbation of the epsilon 0 of the parameters, electromagnetic parameters, hopefully this will give us a generalized eigenvalue of an energy below the essential spectrum. There is a point, there is a problem, which is the problem I told you before, that we need to work in this phase. So not with epsilon 0, but with the new epsilon ball mu, the one that encodes the initial perturbation, perturbated geometry. So we don't want divergence of f to be 0, which is true in the sense this is immediately seen. Divergence of f is equal to 0. But we want divergence epsilon f to be 0. And so what we do, we correct f. So we consider a weak solution of this Dirichlet problem here. And okay, let me mention that the difficulty now is to estimate, to have a good sharp upper bound in the L2 epsilon norm of this correction term W, which is not easy. And what is the challenge of this step? And this is because by the Pythagorean square minus the normal grad of u. So the small, so we hopefully go below these thresholds. Okay, but a lot of calculations after. Okay, I will just present to you the result. So to present the result, I need to introduce some terminology. Psi, again, is a normalized eigenfunction associated with lambda to m, the first non-trivial non-Laplacian eigenvalue on the cross section. Then we introduce these two vector quantities. So capital X is a 2D vector, depending only on the cross section, on the shape of the cross section. It's just the integral on the boundary of the cross section of its normal times psi squared. Psi is this. And then this other vector function. It's a function depending on S, but it only sees the curve. It doesn't see the curve, the cross section. It's basically a rotation of the B-shaped curvatures, the one that define the relatively parallel frame along the curve through which we constructed our waveguide. And thus, with that, so we are in the case, as I told you, of a purely bending waveguide. So theta prime is 0. There is no twist everywhere, anywhere. If the curvature, okay, again, we need another assumption, the curvature between L1. If this inequality holds, then the discrete spectrum is non-empty. So there exists at least one finite dimension, one isolated eigenvalue of finite multiplicity. So here B is the diameter of our cross section. And if you recall, this assumption 2 tells us exactly that 1 minus BK L infinity is strictly positive. So this makes sense, side is positive. So I want to comment about, I will comment now on this condition, but let me mention this recent paper came out on arXiv a few months after ours by Anne-Sophie Bonabendia, Lucas Chanel, Sonnequist in Paris, Institute of Einstein in Paris. And they also deal with the trap mode, so eigenvalues of the electromagnetic waveguides. It's a nice paper, and it's complementary to ours because they use other type of geometric deformation. I told you that our bending and twisting preserve the cross section, but they will, for example, create a bump that will, so they will deform also. They will deform the geometry of the cross section. Or, for example, they consider a half infinite waveguide with a finite resonator attached with it. So it's very nice, and I would say it's very nice because it's also complementary to our paper. So some remarks on this condition that we found. Well, it is necessary that both these vector quantities, so this is the inner scalar product between the two, they must be non-zero to be able to make use of this sufficient condition. And also, since we are in the case of zero twist, so theta is a constant, theta prime is 0, theta is a constant, which means that this quantity here, which is the rotation of K1, K2, the rotation of theta, theta is constant, so we can bring it up, it doesn't depend on that, we can bring it out of the integral, which means, you know, we have this now, this becomes a vector, and we rotate it. So if we are able to choose this constant, there is an so in the sense there is an optimal choice of theta star, call it, maximizing this quantity because we can make the two vectors collinear, pointing in the same direction, parallel in the same direction. In particular, if they're both non-zero, to make this positive. So it means that there exists an optimal way to attach our perception to the curve, optima in the sense to be able to use our sufficient condition, ensuring the existence of the eigenvalues. But let me show you that there exists an infinite class. Actually, I mean, there are actual concrete cases where this holds true. Otherwise, it would not make sense. So assume that we are given a cross section for which x is different from 0 and a curve for which this integral of the curvatures is non-zero. Again, there are examples of it. Now we can stretch the curve. So if you have a curve, or let's say you zoom in on the curve. So if a curve is curving a lot, bending a lot, but you zoom in, you will see less and less curvature. So this is the idea. In fact, the curvature, they will scale by the parameter delta. Delta is a small parameter, small positive parameter. They will scale with delta in front, both the K1, K2, and the actual curvature, kappa. So when you integrate, this combines perfectly with the change of variables. For example, if you take the L1 norm, so these quantities will not vary. And so if you recast your geometric condition for now this slightly curved waveguide built with this, thanks to this new slightly curved curve, you will see that these two quantities, as I told you, these integrals and the integral, because the normal one is an integral, they do not change. But the L infinity normal, the curvature, will scale with a parameter delta in front. And so if delta goes to 0, the right-hand side goes to 0. So eventually, this condition will be satisfied, which means if we are given a curve having this property, so this we show in the paper planar parabola. For a planar parabola, this is true. And if we are given a cross section for which x is not 0, this vector is not. As also a triangle. Then we can always build a waveguide, actually an infinite class of slightly curving waveguides trapped in electromagnetic modes. So really, this can be applied. Now, let me, last few minutes, comment about this geometric condition x different from 0. X, which I call it here, is this 2D vector quantity depending on only on the cross section. So one can just by integration by parts and divergence theorem recast it as a volume integral. So most of the domains for which we can compute, normal Laplacian eigenvalues and eigenfunction explicitly, usually they present a lot of symmetries. For example, this rectangles probably is they are the most simple, and they give us x equal to 0. So if it's like if it's too much, this domain have too much. The domain, the cross section small omega has many symmetries, then our x will be 0. So we cannot apply our condition. And in fact, we prove a result that if the second non-Laplacian value is simple multiplicity 1, and the domain presents a rotational symmetry, which means there exists a center, you rotate, of course, by a non-trivial angle, and you have the same shape, then x is 0. And so, in fact, you can prove indirectly that these kind of rectangles have x equal to 0 with this result. But as I told you, there exist explicit geometries. I mean, explicit in the sense you can compute lambda 2n for this explicitly, and also its Zaccaron function. This is by mirror symmetry, actually, for which that gives x. I mean, x non-zero, so geometries that we can use for our condition. And also we performed a bit of simple numerics. 0, I'll just show you an image of, I produced a Dumble domain in free form, then with the mesh, and then you compute this, solve the normal problem, you compute x. I mean, this as x different from 0, or for example, maybe more interestingly, for a rectangular cross section. Waveguides in application. For example, so for the rectangle x is 0, but if you slightly perturb its shape, so you destroy its symmetry. For example, here you create a bump on each side. So when you keep the rectangle by you this side in blue, you can see that x is different rectangle. You can see that the x activates. It feels like the condition x of the cross section. We prove this rigorously at the radical proof of that. Destroy the symmetry of it, then x activates, then we hope to be able to use our condition. And so to conclude, because these are the main results present in this paper that is currently on archive. And okay, we're given a structured essential spectrum, existence of discrete spectrum, but there is of course a lot of stuff to do. For example, we want to do more actual numerics on a curved waveguide. Or, for example, you can one needs to deal with the case of twist non-zero for the discrete spectrum. Are there some geometrical configuration ensuring that there exists no curve mode? So this is a reverse question. Offset in the vacuum or air, but there exists an embedded obstacle inside, so you can model it as a change of parameters of the epsilon mu. So like you have a scattering object, and you send a wave, electromagnetic wave at a certain frequency, and want to see if an observer on the other side, capturing the far field data that scatters from it, will not see the obstacles. So in the sense, at that frequency, maybe if you modify slightly the geometry of the waveguide near the obstacle, maybe you can make the wave pass through without any scattering. In the sense, there is full transmission and no reflection. So these are these kind of questions, and actually what we're trying to do with the people in Marseille, we are doing some asymptotic analysis of thin waveguides. So when we scale our cross section by a parameter alpha, that then you make them to zero. So you have your waveguide that shrinks, is geometrically reduced to the underlying generating curve. And you want to see if there exists an effective operator at the limit. So a 1D operator may be easier to analyze, to know its spectrum. Maybe this gives us information about existence, localization, nature of the eigenvalues of Maxwell eigenvalues in electromagnetic waves with the thin, very, very thin cross section. And so I finish here.